Hey, welcome to The Explainer. Okay, let's talk about bias in AI. You hear that word a lot, right? And it almost always sounds bad. But what if I told you that inside an AI's brain, bias is not just a good thing, it's essential? Yeah, it's one of the most critical tools an AI uses to actually learn. So let's unlock what's really going on here.
All right, here's our game plan. First, we're going to clear the air. We're not talking about that kind of bias. Then we'll zoom in on what it does for a single neuron, peek at the super simple math involved, and then see it in action with a real example. Stick with me and you'll get why this little number is such a massive deal in AI.
Okay, first things first. We have to get on the same page about what bias even means in this context. Because when an AI engineer says bias, they're almost certainly not talking about what you think they are.
So, on one hand, you've got social bias. That's the human stuff, our prejudices, and preconceived ideas. We're putting that completely aside today. What we are talking about is neural network bias. And what is that? It's just a number. It's a mathematical knob that the AI can turn up or down all by itself to help it find the right answer. That's it. Nothing more, nothing less.
So, if it's just a number, what's its job? Well, you can think of it as a personal on switch for every single neuron inside that huge network.
At its very heart, bias is kind of like a thumb on the scale. It's just an extra value that gets added in to help a neuron decide, should I fire right now or should I stay quiet? It basically sets the default level of excitement for that neuron. Is it eager to fire or does it need a lot of convincing? That's what the bias controls.
And here's what makes this so powerful. Every single neuron gets its own unique bias. But, and this is the kicker, a human doesn't program this in. It's a learnable parameter, just like the weights. The AI figures it out on its own. As it's training, it's constantly tweaking and adjusting these biases, trying to find that perfect setting that makes the whole network better at its job.
Okay, so we know it's a number that gets added, but where? The timing is actually super important. Let's look at where it fits into the equation.
This lays it out perfectly. So first, a neuron gathers all its incoming signals and multiplies them by their weights to get a weighted sum. That's step one. Then, right after that, and this is the key moment, it adds its own unique bias. Only after that bias is factored in does it move to step three and make a final decision. Do I fire or not? That one little addition in the middle changes everything.
I know, this might still sound a little theoretical, so let's make it super concrete. We're going to walk through a really simple example, and you'll see just how dramatic of an effect this one number can have.
All right, picture this. We've got a single neuron. It's getting two signals, or inputs. The first input has a value of 1.0, and its connection has a weight of negative 0.55. The second input is 2.0, with a weight of positive 0.10.
So the first thing the neuron does is calculate the weighted sum. We just multiply the inputs by their weights and add them up. So that's 1 times negative 0.55 plus 2 times 0.10. Do the math, and you get negative 0.35.
Now, let's say this neuron uses a really common activation function called ReLU. You can just think of it as a gatekeeper with one simple rule. If a number is positive, let it through. If it's 0 or negative, block it and output 0. Since our sum is negative 0.35, the gatekeeper blocks it. The output is 0. The neuron does nothing. But what if the model needs this neuron to fire in this exact scenario to get the right answer? Right now, it's stuck. Its activation point is locked at 0. How do we give it the flexibility to fire even when the initial sum is negative? You guessed it, this is where bias saves the day. Let's imagine that through training, the network figured out that a bias of plus 1.0 would be really helpful for this specific neuron. So we just add that to our calculation. Okay, so our original weighted sum was negative 0.35. Now we just add our new bias of 1.0. The new result? Positive 0.65. And boom, that's the magic. Now we have a positive number, 0.65. When that goes to our ReLU gatekeeper, it says, yep, you can pass, and the neuron fires, sending a signal of 0.65 onto the next layer. The bias completely flipped the switch. So, that's a cool little trick for one neuron, but why is this such a big deal for the whole network? What's the grand purpose of this? It really boils down to this one word, flexibility. Bias is what gives a model the freedom to learn much more complex patterns. Without it, the model is way too rigid.
So let's wrap this up. Here's the key takeaway. Bias lets each neuron learn its own custom activation threshold. Without it, they're all stuck at a fixed 0 point. This flexibility is absolutely critical for the model to actually learn from real-world data. And remember, the model learns these values itself. No human is sitting there setting them by hand. It's what makes the network adaptable and, well, smart.
And that kind of leaves us with a final question to chew on. We spend so much time talking about the complex weights connecting all these neurons. But how much of an AI's real power comes from something much simpler? From simply learning when to listen and when to speak?